Active implants monitor and support bodily functions. They send impulses for hearing, heartbeat, and electrical prostheses. Their future development is about miniaturization and energy supply, which in the future will no longer be in the implant, but outside the body. These are systems, implants, which have a coil, a few discrete components. That means very highly miniaturized implant electronics, and here the complete intelligence sits outside the body. Extracorporeal electronics worn on the body then control the stimulation and the synchronization completely from the outside, and thus I can miniaturize these implants extensively. A full implant, which really has many system components, already has a diameter of about 20 millimeters and a height of about 5 millimeters. If I have a highly miniaturized implant, then I can safely pack it in a thin silicone tube, supply it with energy from the outside, and then we have just a few millimeters that we have to place there on the implant. The way in which energy is supplied depends on the type of application. If a system has life support functionalities, for example, then I cannot supply such implants with energy wirelessly from the outside, because an external supply is simply too error-prone. I must ensure that such an implant runs autonomously, and I can only guarantee this if I have an internal energy store. In the interests of maximum miniaturization, and to simplify the approval process, however, I would always like to dispense with this internal energy store. An established method at this point is inductive coupling. The technical limitations here are due to the fact that a near field is very strongly dampened by the body, and then I have to position corresponding coil pairs very closely to each other. However, the Fraunhofer IBMT also has experience with energy injection via ultrasound. The advantage of ultrasound is that due to the good coupling of the transducer to the body, I can also supply very deep-set implants with energy. I can also penetrate titanium housings with ultrasound. Even in each individual active implant, functionality and energy supply must harmonize perfectly. The Fraunhofer IBMT is also conducting research on entire implant networks. Our idea is to implement each sensor and each actuator as a self-contained network implant. The sensor and the actuator are completely integrated into the housing, and I can completely dispense with cable connections. This significantly increases long-term stability. I can replace a self-contained implant much more easily by means of a remission intervention than is the case with a central implant, which may also have a very large wiring harness. However, there are still a number of hurdles to overcome before such active implants can actually be used as a product. This applies to the energy supply, for example, whereas before I only had to supply one implant electronic system with energy. Now I have to supply an entire network of implants, and each implant has its own individual energy requirement, which also changes significantly over time. The next challenge is communication, where before I only had to communicate between an extracorporeal and an implanted component. I now have to route data and commands through an entire network. And when the application demands real-time capability, it gets very complex very quickly.